I'm going to ask you guys to do an experiment while we do this. Okay, so first thing I want to do is we need to define some words. So we need to define a random variable and we need to define our probability distribution. So a random variable is a variable whose values are numbers determined by the outcomes of an experiment. And it probably doesn't really make a lot of sense right now, but it will make sense as we do this experiment. Okay, then we have a probability distribution, and that's a function which maps each value of a random variable onto its probability. So basically, in a probability distribution function, we are taking the random variable, which we'll call x, it's our independent variable, and we're mapping it onto the probability. So your inputs of that function are going to be the random variables, and the outputs are going to be the probability of those random variables. Alright, let's consider rolling two dice and adding the values on the top faces. I want to find the probability of getting a sum of 2. So I'm adding those two values. I get a sum of 2. That's going to be 1 out of 36. The probability of getting a sum of 3 is 2 out of 36. And again, you can just find all this on your dice chart. Okay, all the sums are along the side here. So if I want to get a probability of 4, that's 3 out of 36. Probability of 5 is 4 out of 36. Probability of 6 is 5 out of 36. Probability of 7 is 6 out of 36. Probability of 8 is 5 out of 36. Probability of 9 is 4 out of 36. Probability of 10 is 3 out of 36. Probability of 11 is 2 out of 36. And the probability of 12 is 1 out of 36. Blech. Okay, now what we want to do is calculate the mean or the expected value of this probability distribution. And this is denoted by the Greek letter mu. Okay, so this is the way that I write mu. Okay, so this stands for our expected value. And when you see that, the formula for that is, we're using our summation notation, and we say the sum of your x sub I times your p of x sub I values from I equals 1 up to n. Alright, and that seems a little confusing, but I promise you it's actually really, really easy. Okay, so what we're going to do is we're going to calculate the expected value of all those probabilities that we just found. So we're going to find the expected value of rolling two die and adding the values on the top faces, or rolling two die in the sums, okay, getting the sum of two dice. So an expected value is basically just saying, what do you expect to happen? What would be the most likely thing to occur? And in this case, it's pretty obvious the most likely thing to occur is 7, but in other cases it might be a little less obvious, which is why we have this expected value here. So to calculate the expected value, what I do is I take my x sub I, so that's my random variable, which for my first one would be 2, so getting a sum of 2. I take 2 times the probability of that, so getting a sum of 2, what's the probability of that? It's 1 out of 36. And then I'm going to add that because I have a sum here. I'm adding up all of these values to my next one. So my next one was a sum of 3. And I'm going to multiply that by the probability of getting a sum of 3, which was 2 out of 36. Okay, then I'm going to take a sum of 4, and that probability was 3 out of 36. Okay, and you're just going to keep going until you get all the way to 12, and that was 1 out of 36 again. You're just going to add all those values up. So I multiply these two, then I add it to these two multiplied, then I add it to these two multiplied, all the way up to 12 times 1 over 36. Okay, you're just adding all those terms up, and when you add them all up, you should get 7. Okay, which makes sense in this case because we know that getting a 7 when you roll two die is going to be the most expected thing to happen because that has the highest probability. Now again, that isn't always necessarily true. Just because something has the highest probability doesn't necessarily mean that it's going to be the expected value. It gets a little tricky. The only reason this one works out so well is because it's perfectly symmetric. But most of the situations you run into are not going to be perfectly symmetric like that. So you have to calculate it out. You can't just guess. Alright, now what I want you to do is I want you to get 2 die, and I want you to perform 36 trials of the same experiment. Now if you don't have die, you can always use your graphing calculator. And some of you that have the newer graphing calculators, there's some formula where you can do a simulation of rolling 2 die. But if you don't have that, you can still do this. Okay, so what I want you to do is go to Math, and if you go down to PRB, you'll see this thing that says rand int. Okay, so it's the 5th one, and it says rand int. That stands for random integer. And what we're going to do is we're going to try to define the values that we want our random integer to be between. Okay, so basically what I want you to do is I want you to think about each one of these random integer pushes that you make is going to be 1 die. So in a die we can get 1 through 6. So what you're going to type in here is 1, 6. Oops. Okay, and then you can just keep hitting enter, and that's going to be your dice rolls. So for me, I hit enter twice, okay, and I got a 2 and a 3. So in my first box on my paper, I'm going to add those up because I'm finding the sum, and I'm going to get a 5. Okay, so in my first box I have a 5. I'm going to hit it 2 more times. I get a 1 and a 6, so I'll have a 7 for my next one. Okay, now some of you may be thinking, why don't I just do rand int 1 through 12? Well, the answer is that wouldn't make sense because that's not actually going to give you the same probability as it would if you rolled 2 die. Because I know that getting a sum of 7 is not equally likely as getting a sum of 2. Whereas if I just plug it into my calculator as 1 through 12, it's going to say that all of those things are equally likely, which we know isn't the case. So don't do that. You have to think about each one of these die as being a random, equally likely event to occur. So we have to do 1 through 6, and then we have to do each die each time. So what I want you to do is finish this experiment. If you need to pause the video, go ahead. I want you to fill in that whole table with all 36 values. Alright, now that your values are all filled in, we're going to calculate the relative frequency for each of your possible outcomes. So remember that relative frequency is different than probability because relative frequency is talking about how many times something actually occurred during your experiment. So let's say that I want to calculate R of 2. So that stands for the relative frequency of 2. So what you're going to do in your table is you're going to look through your table and you're going to count all the times that you got a sum of 2. Okay, and we have a total of 36 things in our table. So let's say you got a 2 3 times, then you would say that this is 3 out of 36 because it occurred 3 times out of your total of 36 trials. In other words, this is just your experimental probability. We're calculating what actually occurred during our experiment. And I want you to do that for all of your values 2 through 12. If you need to pause the video, go ahead. Alright, now what we're going to do is we're going to find the mean sum of your relative frequency distribution, which is denoted by x bar. So x bar, that's your mean sum. Okay, essentially what that is I just want you to calculate the expected value of your relative frequency. Okay, so remember earlier when we calculated expected value, it was just 2 times 1 out of 36. So this was my random variable, and this was the probability of that random variable. So that's basically what you're doing here, except you're doing it with relative frequency. So my 2, the probability of getting 2 in my experiment was 3 out of 36, so I would start out with 2 times 3 out of 36 plus, Okay, and you do that all the way up to your 12. So whatever you had for 12, let's just say it was 2 out of 36. Okay, so you add all those terms up, and that's going to give you your mean sum. So again, the mean sum is just calculating the expected value of your relative frequencies. Alright, take a minute to do that. If you need to pause the video, go ahead. And then the last thing we're going to do is we're going to find the percent error, which is x bar minus mu over mu. AKA it's going to be your mean sum minus your actual expected value divided by your expected value, and that's going to give you how far off your experiment was. Okay, so I'm not going to really show you how to do that because I hope you can figure it out. You just take your x bar value that you got minus 7 divided by 7, and that'll give you your percent error. And then normally at this time we would talk as a class about what your percent error was, and hopefully everyone's was pretty small, but sometimes we get people with crazy percent errors. So you just need to remember that theoretical probability and experimental probability are two totally different things. And just because theoretically you're supposed to get a 7 every time doesn't mean that it actually happens that way in real life.